financed by EUMETSAT, but we can still discuss maybe in some future about that as well.
Okay, thank you. Seems there are no more questions. Then thank you, Natasha. Thank you very much. And we can move on. The remaining time until 14 UTC, now 15. I'm always a bit cautious, so it's now 15, it's 14 UTC, so until 15 UTC, that should be correct now. We will spend on the practical side of a forecaster life. Tomasz Pucik is our senior trainer here at the ESSL. And let me unveil, as an exception, please, a very private detail, but I think it's an absolutely positive private detail. Tomasz became father of a really, really cute baby girl a few days ago. So congratulations and all the best for your young family.
Yeah, thank you very much.
While the virtual applause is taking place, I can say that we plan this part in an interactive style now. For that, you can use the chat and I will read out your answers so that Tomasz can concentrate on the displayer. I think we shall now start with your part, Tomasz.
Yeah, Alois, I was wondering, do you think it's a good idea to have a break till 05? Or shall we go on?
It was not planned. Last time it went well without, but okay. I think better continues so that people are not confused if there is nothing happening then for some time here. But let's think about this for next time. Good suggestion.
Sorry, it was just a suggestion that came. It's not that I do not want to present. Okay, I will share my whole screen with you guys. And well, first I'm going to do a presentation. So I have a PowerPoint and then we'll go to the displayer. So the first thing that I'm going to ask, can you see my screen? Yes?
Yes. Yes.
Very good. So I will start my slides. Okay, so before some training material reaches you or before some products related to the satellite or the model or the radar or otherwise reaches you at the testbed, there is typically some discussion and research behind it. So now I would like to present you a little bit of what is going on behind the scene before you actually see some product at the testbed. And Alois has already presented that we have a number of these workshops that we do on the different topics concerning severe weather. And here I will present some material concerning the lightning imager data and what we have found very recently about this and how it may affect the training material that you will get from it. So I will reveal some information about it. And in here you can see a quite interesting group photo. So as you can see, this was a hybrid event, but everyone seems to be very happy about the outcome of the workshop at the end. And well, you can see also some people who have presented here, especially in the bottom row. So we've had personnel from the EUMETSAT, the trainers from different countries, but also researchers. We had for example, we had a person that does a lot of research about lightning from the physical perspective, has looked a lot at the lightning mapping array data. Then we've had a person that worked with lightning jump algorithm applied to the satellite-based lightning detection over the United States and so on. So we're trying to gather enough manpower, both from the trainer perspective, from the EUMETSAT, so from the technicians perspective, so the people who are actually working on the lightning imager and are doing validation of it. And then also we are trying to recruit the personnel from the researcher point of view, so people who can tell us more about the physics or about the patterns that we see in the data. Okay, so what are we workshopping about? There are a number of things from the lightning through moisture, mature convective storms, convective initiation. We also, of course, have a look at the sounding data from the infrared sounder that is coming up in the next couple of years. And we'll talk about the lightning one here. So what are we trying to find out? So when we go to the workshop, We typically set the number of the topics, we do some presentations, and then we also look at the case studies. So we looked at the 3 case studies. Now I will present one of them to you. And the first thing we do is that we just go through the data. Is there something obviously going wrong with the data? So are there any major issues that we need to solve as soon as possible? So let's say first quality check, we get the report from the technical, technical personnel that is working on, for example, the lightning imager to report their first findings about the detection efficiency of the imager and so on. Then, of course, what is a very important question, especially to you forecasters, how can we use the data for nowcasting, for example, storm initiation or storm severity? So this is something that we want to see. We typically look at the number of the products, and we're trying to select those then which are the most useful for the forecasters. So we look at the situation from the perspective of multiple different products, for example, based on this lightning imager data, and which make most sense to us. Of course, what is very important, how to best combine the data that we are looking at. So in this case, the LI data with the other data sets. So of course, as you as the forecasters are not just going to be looking at the lightning imager data the whole day. So we need to make sure that we find out where the lightning imager data really shines most and where it will supplement the other data sets very well. So for example, the radar or the satellite imagery. How to visualize the data. So this is always a big question, and a big part of the discussion in this workshop is about the visualizations. There are typically a number of the proposals that we go through. This is also where you as a forecasters can give us a lot of feedback at the testbeds. And also we are trying to identify the areas where we need to do more in-depth studies. So we are trying to run through these questions at the workshops. We formulate some conclusions, some tasks, and then we have another workshop, something gets tested at the testbed, and this is how it works. So let's have a look at the case. And so we have 3 days of this data, 24-hour data for the lightning imager. And I think we got pretty lucky with this. Well, some people got unlucky because of the severe weather on the day, but there was a lot to test the LI data on in this particular day. So let's have a look at this. But before we proceed, I have a task for you. So let's indulge ourselves in, let's say, this profile. So when you come to the testbed, this is a tool that you will be working with a lot. So the sounder, so the soundings from different models. And you can see we pick the grid point that is shown on the map. I will switch on my laser pointer. So we select the grid point from here. You can see Cape and shear overlap over northeastern Italy. And so this is an ECMWF-based sounding. This is a SCUT profile. So green curve is the dew point. The red is the temperature. Orange is the parcel curve for the most unstable parcel. Well, actually here it is mixed layer. In this case, then you have different shear metrics calculated. This would be storm relative helicities in these different depths. Then we have shear or bulk shear between 0.6, 0.3, 0.1 kilometer. In the right top part, you have a hodograph. Now, there are 2 questions that I would like you to answer. So let's start. We are talking about the lightning. So do you think we can get a lot of lightning here in the storms? Yes or no? And why? You can write either yes or no, which is okay, but I love to hear your reasoning behind this. So let's take a couple of minutes for this, or 2 or 3 minutes, before you have a good look at this. Would you expect very lightning active storms in this case, or not at all?
So far, people are quite shy. No answers yet.
Have we started with a nasty question? I hope not.
No,
they are
no,
just
it's coming.
Just thinking. They're just
now
thinking.
It's coming. Yes, large and deep instability. The top is over -20, so lightning is possible. There's one answer. Yes, major instability. Yes, see, yes, lots of energy. Photograph helping much? Yes, 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 yes.
Yes, yes.
Large
lot
part
of
of
yeses.
storm cloud above freezing level, much lightning because of high cape and much shear. Yes, very high EL. Yes, and supercells. Yes, yes, quite a lot of cape. Quite dry atmosphere and hail ice Bergeron effect is one answer. Yes, high liquid water content next to ice and grapple. If there is growth, the convection is initiated, then yes. Yes, if there was enough lift. Yes, high EL, strong buoyancy. Good hodograph for supercells. The -10 to -20 is in the middle of the cloud. One person is now saying no.
Yeah. Finally, someone disagrees.
Yeah.
There is some variability. Nice. Okay. Are the answers still incoming?
No, now that's
Okay.
it, I think.
So let's put a stop to this and now assess the severe weather potential and expected hazard. So would you expect some severe weather to happen with your storms that either produced a lot or not a lot of lightning, even though most people said yes? And which types of severe weather would you expect just from this profile and sounding? By the way, a question that you would get asked really a lot at the testbed.
First answer is yes, high cape and shear.
Mhm.
Yes, large to very large hail. And maybe bow echoes, question mark. Very large hail possible.
Mhm.
Large hail, very large hail. Strong straight line winds and large hail. A supercell. High shear 1 to 6 kilometers, but 0 to 1 kilometer very large hail. Large hail, strong wind gusts, large hail. Very large hail and severe wind gusts. Large hail, MCS formation, bow echo. Strong wind and large hail, heavy rain. Yes, large hail, large hail and strong wind.
Mm-hmm. Answer still incoming or not?
A few. Some are still coming in. Hail, straight line damaging winds and hail. Large amount of small hail and large hail and heavy downpour. Next answer is supercells and quasi linear convective systems. Heavy rain, strong wind gusts, large hail. Next is tornado. Then strong wind and large hail and heavy rain, no severe winds, large hail and wind shear. That's it, Tomasz.
Wow. First, thank you very much. That's what I like. A lot of interaction. I'm happy that a lot of people were not shy. Okay, let's take it from the lightning and then let's have a look at severe weather. There is a high potential for a lot of lightning to be happening with the storms. And I think that majority of you also wrote a very good reasoning there. So first of all, we really have a lot of cape and also quite fat cape profile above the -10 degrees or above -20 in the zone where we get a lot of charging in the storm. So a big part of the storm will be in the region where we can get these charge centers and charging in the thunderstorm, so we can get a lot of lightning. There is a lot of cape. There is also a lot of moisture available, so we can get a lot of precipitation particles within the storm. Very good. And yes, I also agree that the well-organized storms will tend to produce more lightning on average because they typically have wider updrafts. So they have typically more volume of grapple. That is the main charging particle. So very good. Why are we talking about this, for example, in the connection with the lightning imager? Well, one of the reasons is that, for example, if we want to use the lightning data to nowcast the severe storms, we also need to understand if the storms can produce a lot of lightning in the first place. There can be some severe storms that do not produce a lot of lightning. For example, if majority of Cape is located in the warm part of the clouds. For example, heavy rainstorms sometimes do not have almost any lightning. So it's good to realize if I want to use lightning for nowcasting of severe storms, I also want the situation to be favorable for storms producing quite a bit of lightning. I mean, I cannot get stroboscopic lightning if there is not a good enough Cape in the charging zone. Very good, thank you. And about the severe weather hazards, well, we can discuss a lot about this profile, but in the end, what is the main point here? As a lot of people have written, there is just a lot of Cape with very strong vertical wind shear. So we have 0 to 6 kilometer shear at 29 meter per second. Yeah, a lot of you also have noticed this long hodograph. So this is a shear profile that clearly favors supercells. We have 70 meter per second in 0 to 3 kilometers. So that's good enough also for bow echoes, which were also well mentioned in your answers. What is not so nice for downbursts or for severe wind gas production, which could be a tiny minus, is that the profile is relatively moist. For tornadoes, what is not so good is that the low-level shear is pretty weak. We can see 2 meters per second in the bottom 1 kilometer. And also the values of the storm relative helicity in the lower troposphere are not so big. For heavy rainfall, what is a minus in this situation? Of course, the plus is that you have relatively moist profile. The dew points is above 22 degrees, quite high relative humidity, but actually below 0 degree, not so much Cape actually. And also the storms, in case they don't train over the same area, they will be moving pretty fast. So you can see the mean storm motion is somewhere beyond or close to 50 meters per second. Okay, so let's see what happened. This is the plot of European Severe Weather Database reports. So what we do at the ESSL is that we collect the reports of severe weather all over Europe. And this is, of course, also the basis of many studies that concern severe weather across Europe. And we are trying to improve on our data collection every year. So you can see that some of the reports are really very dense. These green triangles are large hail reports. The yellow squares are severe wind gusts. The blue circles are heavy rain reports. There is no report of tornado, which would be an upside down red triangle. We have some damaging lightning events in here. But what you can see, it was a really big situation starting over France, Switzerland, southern Germany with a lot of hail, then quite a bit of big hail also over Italy, and then a transition, as you have very well spotted, into a there was a big potential for development of bow echoes, and this is actually what happened. We had a major convective windstorm going from Italy through southern Austria and Slovenia into Hungary. What was very interesting is that the system reached peak intensity around 1 or 2 UTC, then decayed or weakened over Hungary around 6 UTC, and then towards 12 UTC or 13 July, it gained strength again and produced more wind gas. So this was a very long-lasting convective system that traveled, I think, close to 1,000 kilometers actually in this case. Well, anyway, just to show you some reports, because of course we want to see what was happening. This was from a supercell over France, hail up to 8.5 centimeters, up to 10 in Italy. So another giant hail case over Italy. There were a lot of them last year, but also the severe wind gusts were incredible. There was actually a 49.6, I think, meter per second wind gust measured over northeastern Italy, and there were 3 more wind gusts at over 40 meters per second that were measured over this area. So quite incredible. And of course, the damage then also corresponds to this. So especially between the northeastern Italy and the western Slovenia, there was also a really quite major property damage to the buildings in some locations. Okay, so this was about the case. Now let's talk about the lightning imager. Well, still before this, we are looking at the satellite data from some storms over France on that day. So what do you see in here? What kind of features?
Overshooting tops.
Yeah, let's see.
V shape. Overshooting tops. An above anvil cirrus plume. AACP, OT, anvil, OT, AACP, AACP, V-shape, OT, V-shape and OT, above cirrus plume, overshooting tops, shoulder worm cold signal, overshooting tops called U, V-shape, OT, AACP, AACP, gravity waves around, overshooting top, OT called U-shape, worm cirrus plume, question mark, IGW, AACP, cold U, above anvil cirrus plume, OT and cold U, flanking line.
Nice.
Now it's stopping.
Now it's stopping. Well, wow, we have experts here. I can just stop presenting, I think. All right. Okay, thank you. Indeed, we'll come back to these features. And now tell me, which of the storms do you think is more severe? This one, let's call it storm west, or this one, which we can call storm east. Let's go.
I am waiting for the first reply. West. West, 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 west. Storm east. West, west, storm west, 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 west. Storm east. East. West. East. East.
Okay.
East, because west will move to low Cape area.
Okay. All right, all right. So yeah, I'm wondering, why did people wrote the eastern storm? So those of you who wrote the east, I'm really curious about your answers. So you can write it down now, if you want, of course, no pressure. You don't need to. Well, we heard one answer that it is moving into lower Cape environment. By the way, there is no Cape field in here. So this is something that we also do at the test bed, or at any of our other courses, that we do ask you for a reasoning of your decisions so that we can discuss them in depth. Okay. Alois, nothing?
Sorry, I dropped out for a moment. I'm now back. I can read out again. So, is it still growing? Question mark. West is in the track of the eastern storm, therefore weaker. West is growing, east is decaying.
Okay. So that is actually a good remark. We do not see a temporal evolution of the storm, which would be much better. Indeed, the trend in what is happening to the storm is extremely important, and we are devoid of this information here. So it is tough to say. Okay, thank you. What about the people that said the west one is the best? So what do you think? What was your reasoning?
Let's wait for the first answers. No answers yet. The first one is colder temperatures on OT. Higher overshooting top, better U or V anvil shape. Western signals are stronger, so stronger updraft.
Mhm.
Slightly darker color means colder temperature. Overshooting top very high. All signatures.
Mhm.
Clear flanking line, well-developed overshooting top, clear environment to the east. The OT seems colder, stronger OT. New cell on west part emerges. More contours in top structures. Maybe more moisture after the eastern storm.
Mhm. Okay.
And better anvil texture.
Better angle texture. You know, it's very interesting that a lot of these characteristics that you have now just mentioned, for example, this texture, there is actually some work being done on quantifying the amount of the texture around the this overshooting top area and using it as one of the severe weather precursors. So we have also tested that at one of the workshop, and we're looking forward to applying it to the FCI data. Okay, very good. Thank you very much. So what do we see in here? Of course, both supercells or both of these storms contain an overshooting top. So in here, well, of course, in the west, it's much more pronounced than in the eastern storm. A cold U signature, so we see these shoulders of colder temperatures surrounding the warm wake area. Again, in the west storm, much more pronounced. And both also have an above anvil cirrus plumes. So the western storm has, again, this AACP more pronounced. The AACP is a shortcut for this above anvil cirrus plume. So this, you can see very beautifully here, you have an overshooting top, an upper level flow coming from this direction, and then the gravity wave breaking, creating this thrust of moisture from the anvil into the lower stratosphere, where it forms this plume above the anvil. Okay, so indeed, the temporal trend could be something. I mean, yeah, you could say that this storm is just developing, but that said, there were some very good remarks that this storm has much more texture. So it's more in, it's in like healthier state. There are more updraft parcels reaching the anvil level. There is a lot of bubbling going on, whereas this storm was still in a supercell mode, but it was already weakening at that time. Flanking line as well. Well, in here, maybe if it was a bit closer to the overshooting top, but indeed there were some new cells developing on the southwestern flank of it. All right, thank you very much. I think that was really good. Congratulations. Now, moving on to the LI data. So we are looking at the flash area for one of these supercells. So actually for this supercell a little bit later on, you can still see this above anvil cirrus plume, and then overshooting top is in here. And the red dots that you can see is the flash area from the lightning imager. So the bigger the circle, the bigger the lightning there is. And we can see a lot of lightning in the flanking line that erupted into a number of new cells that are producing quite a lot, large lightning strikes. And then within the supercell, we can see a ring of very small flashes that surround the overshooting top. And now this is pretty cool. So I will ask you here, what do you think? We said this will be very interactive, so don't put your hand away from the keyboard, please. Do stronger storms typically produce bigger or smaller flashes? What do you think? Or what would seem natural to you?
Curious to see the first answers.
Yes, who will be the first one?
Bigger. Large amount of small flashes.
Mm-hmm.
Bigger flashes. Not typically. Smaller flashes. Bigger flashes. Bigger. Bigger.
Bigger.
Bigger. All of them. Both.
Mm-hmm.
Bigger. more number, higher number, more flashes, smaller flashes. The new ones produce bigger flashes, bigger. Bigger, but the next is smaller flashes. Locally is bigger. Okay, I think now it's
Okay.
One more answer. Big flashes are related to positive lightning from anvil area.
Okay. Yeah. All right. So let's dig in this case a little bit. Bigger doesn't always mean better or stronger storm. And actually, for example, based on the research that has been done in the US concerning their satellite-borne lightning detection system, it seems that the most active storm cores produce very frequent but relatively small flashes. So this is also something that we can see in here. Now, one of the reasons for this, so we are still, of course, finding out more about this, is that when we have a very powerful updraft, there is a lot of turbulence around it, and you have a lot of eddies and the charge usually resides within the core of these eddies. And so around a very powerful updraft, you actually have more, but of smaller charge centers. So we can get more lightning, but typically the flashes are smaller. You can actually see sometimes when you look at the time-lapse videos of supercells, you can see these very frequent, but very small discharges between the updraft tower and the anvil. So this is something that we can even observe visually, not just from the lightning detection system. So that is one thing. And this is also something that we have found for this case when going through the data for different storms. And then we also notice this hole in the lightning activity where the overshooting top is. Now, there is actually a feature that is called the lightning hole in the literature that refers to the physical property of an updraft when the core updraft of the supercell is too powerful for the charging to happen. So all of the precipitation particles are lofted very rapidly into the anvil so that the charge is only deposited around the flanks of this very powerful updraft, leaving the core of the updraft devoid of lightning activity. We do not know exactly if this is what we are seeing here, because as one of the lightning researchers that we talked to during the workshop said, this feature called lightning hole typically refers to the feature observed by lightning mapping arrays, but at a smaller scale of 4 to 5 kilometers across. Now, this would be slightly bigger than that, but still it can be this feature. Of course, it can also be that at this point, the cloud deck, I mean, this is a very deep and tall storm that can have overshooting top that is also 3 to 4 kilometers high. So the cloud deck would be too thick for the lightning imager to see the very small flashes within the core of the storm. So we are trying to find out which of these is the case. So still quite a lot of exciting work to do. Now let's move on to the windstorm part. So we looked at some of these French hailstorms. Now we have this huge anvil. As you can see, the active part of the storm is down here. And we can see the ESWD reports again. So all these yellow squares are severe wind gust reports. We also have some weaker storms over Slovakia and Hungary. And here we have, again, the flash area from the lightning imager. This looks like some kind of a monster in here, right? Or a face of a monster with two eyes. But these are actually two big horizontally extensive flashes happening in this less active part of the storm. And then we have the more active part of the storm in here, where we have this severe wind gas production. Even you can see this arc in the lightning detection, which related to a bow echo that was just crossing Slovenia. So those of you who called for bow echo, congratulations, because it indeed materialized in this case. So once again, the most active storm cores have frequent but relatively small flashes. Of course, we need to test it in more cases and in the different settings to see if this is universally acceptable. Now, another thing that we are looking at the workshop is the comparison between the different lightning detection methods. So the LI works with detecting the optical signal from the lightning, whereas the ground-based networks work with the different parts of electromagnetic spectrum. And sometimes you can see contrasting behavior between different networks for the lightning detection. And we are trying to find out if this information, if we see contrasting behavior, can this be used in the operations? So here we have storms over Italy. And again, we see these flash areas that are a little bit blended out. This is from the LI. And then we also have squares plotted here. So yellow squares are the GLD 360 detections. And so are the blue squares. They are just opposite polarities. So the blue is negative and yellow is the positive polarity. And we can see that we have a storm where there are not so many LI detections, more GLD detections, and also the GLD detections are mostly of a negative polarity. And on the storm to the west, we have more LI detections, a bit fewer GLD 360 detections, but most of them are positive. So you see we have two storms going after another, but they have different polarity, different lightning frequencies, but also different sizes of these strikes. We can see that the western storm has, on average, bigger lightning strikes than the storm in the east. And this is something that we are asking ourselves. So can this combination of these two networks be used to detect anomalously behaving storms? And are these anomalously behaving storms more prone to produce severe weather? And there is some research that suggests that yes, but of course we need to do more research into this. And also, how can we complement these lightning detection networks with each other? The LI gives us information about the area, the duration of the flash, and its radiance. The ground-based networks can give us information about the polarity of strikes, the type of the strike, intra-cloud versus cloud to ground, and also the peak current of the lightning that is being produced. So what if we complement this information? Or what if we use both together? Can we combine them in a very useful way so that we can distill a lot of information about the severity potential of the storms? So this is also something that we would like to work on. So in the end, there is a lot to check. Also, just looking at the LI data, because as I said, we have the information about the area, duration, and radiance. And then for the entire flashes or the groups of events, then there are also put together for the flashes. And we can derive a number of products from these. And we have been looking at a lot of these products during the workshops. And our goal is to narrow this down to a smaller priority list that we will give to you, forecasters, eventually. Of course, there is a big question about the visualization. So whether we plot each flash where it happened and its properties. So each flash is represented by one symbol, or we make grid-based products. So we calculate a property or some quantitative characteristic per grid. So for example, density of flashes per tens of kilometers squared or per kilometer squared. What is the average flash size or the minimum flash size? What is the average flash duration per grid? This is also something that we are trying to find out what would better suit forecasters, the point or the grid-based products. Or we can combine both approaches. And I'm not sure if we have Peter still here. Peter, do you want to tell us something about this product that you have, or this visualization that you have programmed into the displayer? And why did you make it in such a way?
He cannot speak now. He can only type into the chat, Tomasz, because he's not a presenter at the moment.
Aha. Okay. Oh, I'm sorry for this. Okay. Well, Peter will correct me. Okay, in the chat if I say something rubbish. All right. So in the end, what we see in here are the individual groups that are plotted in these colors. So you can see these horizontally extensive strikes that are happening in the stratiform region. And then if the number of the groups of events exceeds a certain threshold, they are plotted as a color, so we can see where the most active storm cores are. So this visualization combines the both aspects, detecting where the lightning strikes are very extensive so that we can see really the part of the cloud where they happen, but also to highlight where the storms should really be most active using this density plot and the scale that you can see here on the right.
Tomasz, I think there is an important question from Slovenia. Are we talking about total lightning? Question mark.
Total. Yeah, I don't. Well, the LI doesn't work in a way that you discriminate the cloud to ground and the intra-cloud lightning. So yes, it's total lightning. Does that answer the question?
All the optical signals.
Yeah, all the optical signals that we can get, yeah, from the lightning. Okay, that's a good question. Thank you. And this is yeah, another plot with the same visualization. So you can see another a big part of Austria under one flash, basically. So indeed, these lightnings in the anvil region of a big convective systems can be huge. I mean, they can be hundreds of kilometers across.
Tomasz, may I interrupt you? Of course, this could be interesting for the question, is there still a lightning threat on the ground?
Yes.
And maybe you can just speak a bit on that.
Yeah, so for example, for the aviation meteorology, it's very important question of when to reopen the airport. So we have a squall line passing, and of course, the most lightning happens in the convective part. So there is a stroboscopic lightning, and then the heavy rain and the wind gust pass, and the lightning activity is ceasing. It is dying down, but still from time to time, these horizontally very extensive flashes can happen, and these eventually often result into very powerful positive lightning bolts that hit the ground, and these are very destructive. You do not want one of them to hit your airport personnel for sure. You would get fired then. So in the end, this can really show that such lightning is happening in the anvil, and that, for example, you shouldn't reopen your airport. Yeah.
There's a question. So these green lines over central Austria are one single lightning?
Yes. That's one single lightning, yes. Cool, isn't it? I think the world record for the longest lightning right now is more than 700 kilometers. And this is based on this satellite-based lightning detection, but I think they detected it over Southern America, I think, from the GOES satellites.
Yeah, I think the fascinating aspect of this data is that we are getting a totally different perspective on the topic of lightning.
Yes.
So that's really a completely different kind of data that we are now looking at.
Mm-hmm. Okay. So, needless to say, we're only at the beginning. The data do look promising, but as I said before, there is a lot to learn more about. How do lightning characteristics change with different types of storms and their hazards? How do LI detections compare to ground-based networks? How does detection efficiency depend on the cloud structure, the geometry, the thickness, or time of the day? And what are the most relevant datasets for forecasters for early warnings of severe weather? So in the end, what we'll do, we'll take some of these products and their visualizations. We'll give it to you, the forecasters at the testbed. We'll be asking you, what do you think about it? We'll have a real-time forecasting scenario. We'll use the data, and let's see how helpful the data will be for the nowcasting of severe weather. So eventually your feedback at the testbed will play a strong role on what we recommend concerning both the LI data usage and visualizations of the product. And well, this was already presented, that we are working continually on this guide on how to use TLI in severe storm forecasting. So after each workshop or after the testbeds, we are updating this. All right, so this is it for now. Concerning the slides, let's see how much time we have. Okay, still some. So I will stop sharing for a bit. Let's see. Very cool indeed. Yes, thank you. Okay, I see that there are no questions, so I will share my screen again, but let's kill the Mr. PowerPoint. And let's go to some other place now. And okay, let's go here. And I would like to talk about another case on 24 July. But before we go to the main show, I would like to ask you something. What do you think about the severe weather potential here? For example, when you compare it to what you have seen over northern Italy for the previous case. What do you think?
The first answer is here, strong winds.
Strong winds.
The others still thinking. I can, in the meantime, answer a question. Is the guide published somewhere? Well, it's not yet ready for publishing. We're still working on it. So it might take a few more months. In autumn, we will review and revisit this guide, but maybe towards the end of the year. So now the answers. Very low LCL, strong SHR, 0 to 1 kilometer, tornado potential, tornado, supercells and large hail, some tornado potential. I'd go for a tornado, question mark, tornado, less cape, but more sheer 0 to 1 kilometer, possible tornado. Strong winds, large hail, tornado, strong winds, tornado, also heavy rain, by the way. Severe winds, strong wind, rainfall, heavy rain, tornado, question mark, giant hail.
Oh, because 24 July is the case, right?
Giant hail during the night.
Yeah. Okay. All right. Thank you. Well, the giant hail didn't happen here. By the way, if we are forecasting giant hail, we would like to see more cape in this part. So the cape is pretty skinny. This is pretty skinny cape. You want to see fatter cape profile for big hail. You want to see a lot of buoyancy being released right in the zone where the hail grows. Actually, there was no hail in the storms here, but there was something. And by the way, while the 24 July is most known for the giant hail over Italy, so I'm not even asking you about Italy because, of course, almost everybody knows what happened there. This was also a very, very interesting case. So I will just animate some of the satellite and radar data. And there was a storm that went from France over Switzerland. Note that on the satellite imagery, you also do not see that much because there is relatively skinny cape in the upper troposphere, so we do not get a huge action concerning the overshooting tops or whatever. But we got more than 60 meters per second wind gust in La Chaux-de-Fonds. I apologize for bad pronunciation. This is a measured values. This was the strongest wind gust that we got concerning convection, 60 meters per second during the last year's convective convective season. This was a very local event. 40 people were injured and 1 person died. There was a lot of damage. So the power lines, the high voltage power lines were overtopped, roofs were destroyed, the cars were overturned. In the end, the damage survey didn't confirm a tornado. This was a very powerful downburst with the supercell, I guess. There wasn't even any, or I guess even more like a linear small sign of a hook here at the end, where the 60 meter per second wind gusts happen. But yeah, Cape wise, when we compare the Cape to the northern Italy from this 12th July, yeah, it was very marginal environment, but then the storm gave 60 meter per second, which I wouldn't expect that. I have to be very honest with you. And my jaw was on the floor. I first thought, I mean, this must be some mistake or something, but no, it really happened, and there was very, very bad damage in the town from the wind. There was more Cape in the south. You can see a supercell here producing a swath of large hail. Of course, the main show is about to start in the Italy, and we are in the afternoon hours, so we are at 15, or I can maybe even go a little bit further. I can go to 18 UTC maybe. So when the show was really starting, or maybe even before that. And one of the things, so when I ask you, what would you consider is more favorable for development of the storms, or where would you expect more storms to develop? So here in the south, where we have a temperature of 32, 31, dew points of 22 here is 26, but yeah, I know that this station is weird. And up north, we have a temperature of 25 and 24. What would you consider to be more prone storm-wise? Where would you expect more potential for severe weather?
So the chat is open.
The chat is open, always.
Maybe you can repeat the question once again.
So what would you consider a more favorable environment, ahead of the cold front, when the temperature is above 30, or behind the cold front when the temperature has already dropped slightly to 24 or 25? Or you can also say, I cannot answer this question.
Northeast Italy.
This is not good to do a case where people know the outcome exactly. Okay. Do we have any more answers in the chat?
No. It's very calm.
Okay. Well, I mean, I have already. You see quite bad storms that are developing in here, and this was a very interesting case because the biggest storms developed behind the surface cold front. So already you can see a colder air over the northeastern Italy. So we see that the temperatures are already 26, 27. I mean, it's still not cool, of course, but towards the south, the temperatures are higher. We can go to 20. And well, I will put the enhanced infrared. Where are we here? The rapid scan. And you can see that the storms in here, for example, this storm that is producing this very large hail, we already have cooler temperatures. It's 23, 24 near the ground. Here, previously it was 30, now it is 24, 20 northerly wind, and we have these northeasterly winds spreading over Italy, and yet we have storms developing just behind the cold front, and they are massive. You can see, maybe I will switch off the ESWD reports for now, and I'm just going to animate, maybe also without the surface without the surface observations. You can see this massive overshooting top in here, right? I mean, this is no question, with a warm wake area. And this storm produced very bad wind-driven hail in Mortegliano in Italy. So this was one of these first supercell. Then the second is here, and it will come down. Basically, it went all the way to Croatia. It hit Istria and then continued further. Actually, overnight, also you can see quite massive overshooting top in here with warm wake area behind it. Super impressive. And now we are moving to towards the 21 UTC. Okay, let me put this in here, and this will be maybe my last question to you. So note the storm development in here, and can you see the time? I hope you can.
Yes,
so
we
I
can.
will let's concentrate on this area here, and you will tell me at what point do you think the giant, let's say giant hail production started, okay? So I'm starting at 20 UTC, and I will go towards 21, and you will tell me at which point, at which time we have 5-minute increments, you would say, okay, there is giant hail happening. Maybe I can go further till 22, why not? So I will start at 20 again. This will be our last thing, last interactive thing together.
Twenty 50, 2055, 2050,
2055.
2040
Yes.
to 2050,
Mm-hmm.
55, 40 to 55.
Oh, looks beautiful here. Definitely.
2045 on. 2050, 2020 and 2050. 2055, 50, 20, 50, 40, 50, 45 to 50. 2100, 2110, 2050.
I understand why. Of course, this looks very tempting. Okay, let's look at the.
And once again, 2050.
Okay, let's look at the ESWD. Yes, 2050 was when the storm produced 19 centimeter hail. That was the time. But it was even before that the storm started dropping very big hail. And you can see already at 2015, we have a report of 4 centimeter hail in here. And then by 2025, we have 5 centimeter hail, and then 6, 2035, and then it explodes. So this is also one of the things. It can be tempting when using satellite for nowcasting to wait till the storm is beautifully developed, when the warm wake area is huge and the anvil has really expanded. But already, I think what gives it away quite a bit is how cold the overshooting tops are getting. And they are pushing through this original anvil from the previous storms. And we can see this rapid spreading of the anvil between 2020, 25, 2030 UTC. Then the divergence is incredible at the anvil level. We get more of these overshooting tops. And of course, this is the prime time for the storm now. So yeah, you identify this beginning of the giant hail phase very, very well.
There's a question.
Yes.
Most reports seem to be south of the overshooting top, question mark. Should
This
we
is
talk
because
about
of
the parallax effect, yeah?
Yes, that's a good question. This is an apparent shift of the storm location that is caused by the viewing angle of the satellite. You have to remember we're looking, let's say, from the side at the storm. We're not looking from the top. And because the storm tops are much higher than the ground, then it seems apparently as the storm was more north than it should be. So that's also a very important consideration if you do not have parallax correction at your satellite data, that you should indeed take care of this. Good comment. Thank you very much for this. One thing that I will plot here by the end, look at the surface observations. Some of the surface observations near the storms, it was 18 degrees or 23 degrees just south of the giant hail producing storm. So this is a relatively cool environment, quite a bit behind the surface cold front. You can see still there are parts of Italy where it is 30, 34, 20, 28. So probably some of you know this, know the term that convection was elevated. So actually, when we check the environment, maybe I can use some higher resolution model, for example, the Icon D2, and we look at the model profile from the area, then you will see that they are showing mostly elevated cape there. So it's rather cool near the surface, but the cape starts somewhere around 900 or 850 hectopascals. Of course, the shear was incredible that day, so you can see very long holograph. Okay, so this is elevated. All of these hailstorms were elevated supercells. It was quite cool near the ground already, but that doesn't mean there is not an abundance cape above this. So also one of the things we always remark to the testbeds, that the fact that the cold front has passed doesn't mean that the severe weather threat has to drop down to zero, and well, it was definitely not zero in here. Okay. Do you have any questions about the case? So you can write in the chat, and in the meantime, I'm going to show you some images of these hailstorms that fell in Italy.
There is one question: orographic lifting from the Alps as a cause?
Yeah, some of these supercells were triggered by orography. Yeah, and then some of them were triggered by this isentropic lift along the front.
Okay, then with these images, Tomasz, thank you very much for these cases, for these examples.
I would like to show you more, but there is a bar here, and well, yeah. So I could. The biggest one is behind share audio. I don't know if you.
Okay, then thank you again.
Anyway,
thank you very much. I will just put the very last slide from my side on here for all of you. It's again the link for the testbed application page on the EUMETSAT training area. I hope that you all enjoyed these 2 hours. Thank you very much for joining. We will make available the presentations to you and the recording, so you can have a look at this or forward it to others. Please give us a few days. We have to review that and to cut the recordings and so on. So it will take a bit, but you will get that. Stefan, I'd like to ask you for the final words, if you like, because you opened your camera.
Okay. I just wanted to open it to say goodbye, but it's been great to have you all here, and I think it was a great mix of background and application through Tomasz. And stay tuned to these testbeds and our activities. I think it's worthwhile. Thank you very much.
Thank you very much, and bye-bye to all of you.
Bye.
Thank you. Bye.